Good day to everybody from South Africa, where a cold front has just moved deep into the interior and winter has arrived. This talk is indeed about exploring how seasonality may impact on COVID-19 infection rates here in South Africa, but also, of course, across the world. I am Professor of Climatology at the Global Change Institute at the University of the Witwatersrand, that is in Johannesburg, South Africa. My field of speciality is the projection of future climate change over Africa and therefore also climate modeling. But like many other climatologists across the world, over the last few months, I've shifted my focus to investigate the potential impacts of seasonality and temperature and humidity anomalies in particular on COVID-19 infection rates. In South Africa, we formed a consortium of environmental scientists that are focused on investigating this topic. We call ourselves the COVID-19 Environmental Reference Group. We are functioning under the auspices of the Department of Science and Innovation in South Africa. And our efforts are linked to the national epidemiological modeling effort in the country. The main question for us is, of course, how the South African winter may enhance COVID-19 infection rates in the country. And that is the critical question right now in the Southern Hemisphere. And then, of course, the other important focus that I think climatologists can bring to the COVID-19 epidemiological effort is our experience in working with scenarios. So climate change scientists, as I'm sure you all know, have a lot of experience in working with large multi-model ensembles of projections of the future, often under very different scenarios. In our case, it's usually low and high mitigation greenhouse gas scenarios that then impact on climate. And in South Africa, we are also then trying to share this experience with the epidemiological modelers. The main algorithm I'll be using today when sharing some thoughts on seasonality had its origins in the early days of the COVID-19 outbreak. It's mostly based on empirical studies performed initially in China, but later also, of course, in Europe and the United States. I'm not advocating at all that this algorithm is the true one in terms of representing seasonality. I am merely using it as an example of how COVID-19 seasonality may manifest in reality. In this algorithm I'm using today, COVID-19 infection rates are peaking climatologically wise between 5 and 11 degrees Celsius. That's when the daily average temperature is within those bounds. And then there's a secondary effect of the infection rate being reduced when the absolute humidity rises to above values of 9 grams per cubic meter. When we apply this algorithm to South African climate, we get the maps that you can see on the screen. By the time that we reach mid-winter conditions in South Africa, June in the map, bottom right part of the map, absolute humidity is so low and temperatures are so low that COVID-19 infection rates are peaking, according to this algorithm in South Africa. So we refer to this modifying effect of climate on infection rates as the climate correction factor. It's scaled as a factor ranging between 0 and 1. In March, when we had the onset of the disease in South Africa, you can see that the factor reaches values of about 0.7 over the South African interior. And that is just because in March there's still a great deal of moisture in circulation and temperatures are substantially higher than in June. And it effectively means that when the disease started in South Africa in March, the impact of climate on the infection rate had the effect of reducing the infection rate by about 30 to 40% compared to the June infection rate. That is now, of course, under the assumption, the very strong assumption of this specific algorithm. And then the situation continues. If it is true that low humidity and low temperatures are boosting the COVID-19 infection rate, then of course it's bad news for South Africa. Our interior is extremely dry in winter. and it's very cold in winter. It's a typical continental climate with warm, cold seasonality. And that means that for the next 3 months, we'll be living in peak infection conditions as far as seasonality is concerned, at least in the interior of South Africa. It also to a large extent to the coastal areas, this enhanced effect of seasonality on infection rate. And it's only when spring arrives with the higher temperatures and the first fluxes of moisture again into the country that we can expect some relief from this effect. This slide just zooms into the seasonal cycle of average daily temperature, top graphic, and the climate correction factor bottom graphic for Johannesburg. Now, South Africa's industrial heartland is centered around Johannesburg. About 15 million people live in this part of the country. We refer to it, it's known as the Gauteng province. And it's a typical continental climate that Johannesburg has. You can see that average temperatures drop to about 10 degrees Celsius in the middle of winter. Absolute humidity is very, very high. It's very, very low, and that translates to this high climate correction factor. That means, in terms of how the algorithm is formulated, peak conditions in terms of climate effects on infection rate. In the last part of this talk, I'd like to show how we've been applying this algorithm within a third epidemiological model to investigate how seasonality may influence the sensitivity of the infection rate. In this model, the infection rate is assumed to have a value of about 0.319. The recovery rate is about 0.16. The rate at which people are dying is about 0.005. All of these values are expressed per day, of course, and it translates to an R0 value of about 2. In the simulations I'm going to show, the population size is 12 million people. The disease starts on the 5th of March with a single infected person. And then 2 non-pharmaceutical control measures are assumed in this model. First, a very strict national lockdown, replicating what South Africa indeed had in terms of a lockdown, that reduces the infection rate by a factor of about 0.63. And then in early May, that changes to about 0.8. That's the time that South Africa started to relax its national lockdown. The purpose of this model is purely to perform theoretical simulations exploring the impacts of seasonality on COVID-19 infection rate. These are the types of output the model produces. If we start with a value of R0 equal to 2.4 and we exclude all seasonality effects, we get the black curve in that graphic. It predicts that in the Gauteng province of South Africa, the infection will peak around about in early July. And you will see that more than 1.6 million people will be infected at the time of the peak infection. This is very much consistent with the current national predictions that are being issued for South Africa. Now, the green curve represents the impacts of seasonality. You can see that there's almost no impact in terms of the amplitude of the peak infection. But the peak infection is delayed by about 1 month. That is purely because under these assumptions of seasonality as we've made them in the work I'm presenting today, the high temperatures in autumn are greatly damping the infection rate. And it's only in winter that the infection really gets going within the South African population. Now, if we consider lower infection rates, for example, for a start R0 equal to 2.2, you can see the same effect. Seasonality delays the time by which we reach the peak infection. But now you can also see a secondary effect, namely that the amplitude of the peak infection is being reduced. In this case, the disease is not managing to reach its full potential during those 3 months of midwinter conditions. And when spring arrives, there's once again a dampening of the infection rate, and that results in a reduced peak infection. This effect is even more clearly visible at even lower infection rates, like in this example I've just added, R0 equal to 2. And then something very interesting happens at even lower inherent infection rates. For R0 equal to 1.5, that thick green line shows the case without any seasonality effects. So you can see that now already the amplitude of the peak infection is substantially reduced, purely because the infection rate itself is lower, and the disease only peaks in early October. But in this case, the dampening effect of seasonality is so strong that the disease just gets going in winter. There's a bit of momentum into spring, and then it gets damped out again by summer. Now in this case, if we zoom into that blue line, not only looking at 2020 but also at 2021, we can see a very interesting and potentially a very important effect. Namely that if seasonality is very strong and on the low infection rates, we can see that the disease has a relatively small peak infection in 2020. It then gets damped out almost completely by the summer of 2020-21. But there's a great enough portion of susceptible people left in the population for the disease to reach a much larger amplitude in peak infection during the winter of 2021. So remember, in this case, the disease keeps on lingering in the population. And for the winter of 2021, there's in fact a larger number of infected people that provides a more favorable initial condition for the disease to develop from in the winter of 2021 compared to the winter of 2020. So to conclude, the main message I'd like to share today is that it is important for epidemiological models to include seasonality in the form of a scenario. So it's important to consider right now in the Southern Hemisphere how winter may be enhancing infection rates. And of course, for the Northern Hemisphere, it's important to take into account that summer is damping those infection rates. But what will happen in the following year if there's still a large number of people in the population that are susceptible? In South Africa, we've submitted a review paper on this topic of seasonality, and I think like everybody else, we've come to the insight that right now there's no consensus and there's no clarity on how important seasonality is, but that's why it is so important to include it as a scenario in predictions, as I've mentioned. There are ongoing inverse modeling efforts within our consortium in terms of exploring seasonality impacts on infection rates. Of course, most of our work is through the lens of South Africa and South African infections. The national modeling effort in South Africa that is informing government policy is including seasonality. So this algorithm I've been presenting and its resulting impacts on the infection rate is being used in our national model that runs across 4,300 different wards in South Africa. And then finally, you can see a link there in the very last bullet. We've also written an opinion piece on how the knowledge of climate change scientists in terms of dealing with scenarios and multi-model ensembles may help epidemiological modelers in their interactions with governments across the world right now. The very last thing I'd like to say is that our consortium CIRC is also involved in an initiative of a big international conference coming up in early August. It will be focused on the meteorological and environmental drivers in the COVID-19 pandemic. All the details on this last slide. I won't mention all of them except that the World Meteorological Organization is going to be the main host, and the main sponsor is no organization else but GeoHealth. The AGU will be the technological host, and there will be various international partners involved. A contact person of Neville Swade of South Africa, who is involved in the organizing committee, is provided there. And I think this is a next international meeting to look forward to, where we can share our knowledge or our insights into seasonality and COVID-19 infection rates. Thank you to Elena and the colleagues from GeoHealth for this opportunity to share some insights from South Africa.